if the two circles touch each other internally, then we have the distance between the centers AB. This time, this will either be equal to R1 minus R2, or it can be R2 minus R1, whichever is greater. If R2 is greater than R1, then we write R2 minus R1. If R1 is greater than R2, then we write R1 minus R2. Okay. Collectively, this is also written as plus or minus R1 minus R2. Okay. Or this can also be written as R1 difference R2. Okay. It is the same thing. Whether you write this or this or this, all are the same. Okay. So that is what you must know from this part. If two circles touch each other externally, then the distance between the centers D must be equal to sum of the radii. And if the two circles touch each other internally, then the distance between the centers must be equal to difference of the radii, R1 minus R2, or you can also have R2 minus R1. Okay. Let us look at this problem, which is an application of this theorem. Okay. Question here is, P and Q are centers of circles of radii 9 centimeter and 2 centimeter. Let's mark. So P and Q are centers of two circles. This is 9 centimeter given, and this is 9 centimeter given. Okay. And Q is another circle with center Q whose radius is 2 centimeter. So this is 2 centimeter, and this is also 2 centimeter. 9 centimeter, and you have 9 centimeter. Okay. This is given. PQ is equal to 17 centimeter. That means this distance is given to you as 17 centimeter. And if you see which circles touch each other, if you see in the figure, the circle with center P and circle with center R touch each other externally. And if you see the circle with center R and circle with center Q touch each other externally. However, what you must note is the circle with center P and the circle with center Q, these circles do not touch each other. Okay. So these you must see. This you must observe from the figure. So this is okay. Next, if R is the radius of the circle, or if R is the center of the circle of radius x centimeter, which touches the above circles externally, that means this radius is given to be x centimeter. Okay. Given PRQ is 90 degrees, so this angle is given to you as 90 degree. Write an equation in x and solve it. Okay. So basically, we have to find out the radius of the circle with center R. So how do you proceed with this? Now, if you see, because the circles with center P and R, they touch each other. If you draw a line joining P and R, this PR line, this line must pass through the point of contact, right? And therefore, the distance between the centers must be equal to sum of the radii. That means what is this distance? X plus 9, right? And similarly here, these two circles touch each other. This is your RQ. Now, RQ is the line joining the centers of the circle with center R and Q. Then it must pass through the point of contact, this one. That means this entire length will be X plus 2, the sum of the radii, right? So what have we got? We have got this distance. We have got this distance. And we already know this distance. Now, if you see PRQ is a right angle triangle. So from Pythagoras theorem, what can we write? PQ is the hypotenuse. So PQ square must be equal to PR square plus RQ square, right? And PQ square, PQ is given to be 17. This is 17 square. PR is, what is the length here? X plus 9. We put here X plus 9. And RQ, what is the length? X plus 2. Okay, so this is an equation in X that we are getting. If we can solve this equation, then we'll be able to find out the value of X. Okay, so how to solve this equation? Expand X plus 9 by A plus B whole square formula, and here also you expand. Okay. Now what you do, you simplify the right hand side. 289 is equal to, you get 2x square. 18 plus 4 is 22. And 81 plus 4 is 85. Okay. And now you take everything to the right hand side, and so that you can make the left hand side 0. So you get 0 is equal to 2x square plus 22x plus 85 minus 289 is equal to 0. Okay. So once you get this, you are getting 0 is equal to 2x square plus 22x, and you have 85 minus 289 as 204. So what you see is that you are getting here a quadratic in x. You get 2x square plus 22x minus 204 is equal to 0. You can take the factor 2 common to get x square plus 11x minus 52 is equal to 0. Okay. Sorry, not 52. This is 102. Right. That means x square plus 11x minus 102 must be equal to 0. So now you can factorize this. 17 into 6. Right. Get a x into x plus 17 minus 6 into x plus 17. That means you get x plus 17 into x minus 6 is equal to 0. That means you get either x is equal to minus 17, which is not possible. Radius cannot be negative. Or you get x is equal to 6 centimeter. Right. So therefore the answer is, what is the radius of the circle with center R? 6 centimeter. That finishes this problem. Let's move to the next question. This is a case where two circles touch each other internally. Let's see what this question states. In the figure given below, A and B are centers of two circles touching each other internally at P. So here, these two circles touch each other. This is the point of contact of the circles. And P is a point, and P and uh, through P we draw a common tangent such that this length PT is 12 centimeters. Okay, BT is 13 centimeter. This length is 13 centimeters. And the radius of the circle with center A, that means radius of the circle with center A means this, right? Is 2 centimeter. So that means this is 2 centimeter, right? Find the distance between the centers of the circles. What is the distance between the centers? This one, right? We need to find out this distance. Now, how to find out this distance? First of all, if I can take the radius of the circle with if I say the distance between the centers of the circle is x, let us say this is x, because we need to find out this distance. That means what is the radius of the circle with center B? This is the radius, which is x plus 2, right? Now you see, because we know all this, this distance here is x plus 2. This distance here is 2 centimeters. Now you see that the radius is perpendicular to the tangent. That means this must be a 90-degree angle, right? And this is x plus 2. So which one is the hypotenuse here? This becomes your hypotenuse, right? And if you see the right angle triangle BPT, BT is the hypotenuse. Therefore, what can you write from Pythagoras theorem? BT square is equal to BP square plus PT square, right? Now, if you put the values here, BT is 13, BP is x plus 2, and PT here is 12. Now you need to solve this quadratic to get the value of x, that is the distance between the centers. Okay, and how do you solve this? So you can simply solve this by writing 13 square as 169, and you have x plus 2 square plus 144. You can solve it as a quadratic, but the easier method would be to keep x plus 2 whole square as it is. That means you're getting x plus 2 whole square is equal to 25. That means x plus 2 will be equal to square root of 25 plus or minus, right? That means x plus 2 is equal to plus or minus 5, right? Now, if you take the negative sign, you get x plus 2 is equal to minus 5. That means you're getting x is equal to minus 7, which is not possible. Radius cannot be, or the distance cannot be negative, right? Taking positive sign, what do you get? X plus 2 is equal to 5. That means you get x is equal to 3 centimeters, right? And we had taken the distance between the centers to be x, and that is what was the question was, to find out the distance between the centers. Okay. So I have used two theorems here. What is the first theorem that I have used? That the line joining the centers must pass through the point of contact. So this must be a straight line, right? And the other theorem that I have used is that the radius and tangent must be perpendicular, that this angle must be 90 degrees. Okay. Fine. So let's proceed with the next question. Okay. This question is, if two chords of a circle intersect internally or externally, then the product of the length of the segments must be equal. Okay. Look at this, the first one, what this theorem means. You can have two chords which touch each other, which intersect each other internally inside the circle at P. Then, if this is the case, then we can write the product of the length of their segment. That means PA into PB. That means this length PA into this length PB must be equal to this length PC into this length PD. Okay. If the circles touch each other internally, then this is one segment here, this is one segment here. So you take the product of these two. Okay. This is another segment, this is another segment. You take the product of these two. They must be equal. Okay. This is the case where the circles touch each other, where the circles, where the chords intersect each other internally. If, however, if you consider the second case, where the chords intersect each other externally at P, this is a chord AB, this is a chord CD, and if these two chords, when produced, they intersect each other externally at P, then also the product of the length of the segment must be equal. So what are they? So you have PA, this length, into PB, this length, product of these two, PA into PB, must be equal to this entire length PC into this length PD. Okay, so when the chords intersect each other externally, then this is one segment, and this entire length is another segment. You take the product of these two. And similarly here, this is one segment, this is another segment. To take the product of these two, products must be equal. You must remember this to solve problems. Okay. This actually comes from similar triangles, but we'll not get into similar triangles. You can actually show the proof of this with the help of similar triangles very easily. But we will only remember the theorem and use the theorem instead of going into similar triangles. Look at this question here. Find the length of, find the unknown length x in each of the following cases. So look at the first question. These are two chords. This is one chord, CD, and this is another chord, AB. They intersect each other internally, right? And what is the point of intersection? Here. This P is the point of intersection. You need to find the length of x. Now, from the theorem, what can we say? This is one segment here, right? PC. This is another segment here, PD. Take the product of these two. Also, take the product of these two, PA. And this is another segment, PB. And they must be equal according to the theorem. Okay. So now you can simply put the values here. Get 3 into 4 is equal to PA is 6 and PB is x. So you get x is equal to 6x is equal to 12. That means you get x is equal to 2. Okay. This is a case where the chords intersect each other internally. The next question here is a case where the chords intersect each other externally. In that case, what happens? If you see here, CD is one chord and AB is another chord, and they intersect each other externally at the point P. In this case, from the theorem, what can we write? Product of the length of the segments must be equal. What are the segments here? If you see, PC is one segment, this segment. What is the other segment? PD. Must be equal to, this is one segment, PA, into the other segment is PB. These two must be equal. Now simply put the values. PC, what is the length of PC? It is 8 plus 9. Okay, PD is 8. PA is x plus 7. Right? This length is 7. This will be x plus 7. Into PB is 7. So what are you getting here? 17 into 8 is equal to 7 times x plus 7. So this is an equation which you can solve easily. So you get x plus 7 is equal to 17 into 8 by 7. That means you get x plus 7 136 by 7. You get x is equal to 136 by 7 minus 7, which is 136 minus 49. Divided by 7. This is 87 by 7. So this is 1, 2, 3 by 7. 12 by 3 by 7 centimeters. Okay. Easy enough. Let us move to the next question. Angles in alternate segment. Now this is one concept that you must know very well, and this is not, sometimes it gets a little too difficult to understand also. What do you mean by angles in alternate segments? Okay. Now the first requirement, what are the angles in alternate segments? Let's see here. Suppose you have a circle. This must be given to you, okay? You have a circle, and suppose you have a tangent to the circle. Let us say this is the tangent to the circle. And you have a point of contact. Okay. And from this point of contact, a chord must be given to you. Let's say this is the chord that is given to you. Okay. So this, for angles in alternate segment, this must be given to you. Okay. This kind of a diagram must be given to you. Let's call this point A. So PA becomes your chord. And this chord must necessarily pass through the point of contact of the tangent. Whenever you have this kind of a setup, then if you see, this chord divides this circle into two segments. What are the segments? This is segment 1, a major segment, and this is segment 2. These are called the alternate segments. Okay. These two segments are called alternate segments. Okay. Now, what is the angle in the minor segment here? We call this angle as angle in the minor segment, right? And any angle that is made in the major segment is called angle in the major segment. Okay. So what I do here is I can construct many angles here. What are those angles that I can construct? But they all must be on the segment AP. Okay. This is one angle I can construct. Another angle I can construct. And many angles I can construct, but all must be on the chord AP. Okay. Then this angle here, this angle, let's call this angle 1. Let's call this angle 2. 1 and 2, angle 1 and angle 2 are angles in alternate segments. Okay. What is the other angle in alternate segment? Angle 1. And also, if I call this angle 3, angle 3 are angles in alternate segments. All these pairs are angles in alternate segments. Alternate segments. Also, if I have this angle as angle number 4, then angle 1 and angle 4 are angles in alternate segments. Right? All these angles, these pairs of angles, angle 1, angle 2, these are called angles in alternate segments. Angle 1 and angle 3, these are called angles in alternate segment, because if you see, one angle is in the minor segment and the other angle is in the major segment, right? Similarly, angle 1 and angle 4 are also angles in alternate segments. Okay. Now, what can be the other angles in alternate segments? Let's see. I have taken this angle as angle in the one segment. Now, suppose again I have a tangent and a chord intersecting each other at P, then this is another angle, right? In one segment, right? And what is the angle? What can be the angles in the other segment? I can have angles like these. Right? If I call this angle 1, this as angle 2, this as angle 3, then angle 1 and angle 2 are angles in alternate segments. Okay. Similarly, angle 1 and angle 2, angle 3 are angles in alternate segments. Right? So I hope angle in alternate segments is clear. Now there's a theorem which states that angles in alternate segment must be equal. Okay. If you have angles in alternate, a pair of angles in alternate segments, they must be equal. Okay. Um, for angles in alternate segments, you must have a tangent, point of contact. You must have a chord that must pass through the point of contact. And again, this angle here, if I call x, in this is angle in one segment, what can be the angles in the other segments? This can be the other angle in the alternate segment. This angle has to be x. What can be the other angle? This can be another angle here. This angle also has to be x. And in fact, any angle that you draw in the major segment, that must be equal to x. Okay. Now look at it from the other point of view. Suppose if I take this angle in this segment, this angle. This is angle in the major segment when a chord and the uh, tangent intersect at the point of contact. This is angle in one segment. What can be the other angles? This can be one angle. So if I call this angle as y, this angle must also be y. I can also have an angle in this manner in this segment. This. And this angle must also be y. Okay. So this theorem states that angles in alternate segment must be equal. Okay. So now once we know what we mean by angles in alternate segment, we should be in a position to solve this problem. Look at this. In the figure given below, PQ is equal to RQ, which is already marked in the figure. Angle RQP is equal to 68. So this angle here is given to be 68. Okay, RQP is given to be 68. Okay, and PC and QC are tangents to the circle. So if you see this PC and this QC are tangents to the circle, what is the point of contact of this tangent? P. What is the point of contact of this tangent? Q. Okay. And what interestingly, what you also notice is that through the point of contact, you also have a chord, right? PQ that passes through the point of contact P and also passes through the point of contact Q, right? Okay. This is one observation that we must make. You need to calculate the values of QOP. So which one is the QOP? This. This is the unknown angle that you need to find out. So how do you find out this angle? First of all, what you must note is that because this triangle here, PQR, this triangle that you see is an isosceles triangle because this side RQ is equal to this side PQ. That means angles opposite to the equal sides must be equal. So which are the equal angles? This angle must be equal to this angle, right? Which you can find very easily. So this angle will be equal to how much? If I take this angle as x and this angle as x, x plus 68 must be equal to 180, right? So you have 2x is equal to 180 minus 68. So how much is this angle coming to? Let's see. This angle should come to 56. So 2x is equal to 112. Means x is equal to 112 by 2, which is equal to 56 degree. So this angle here is 56. This is 56 and this is also 56. Fine. So once we know this angle to be 56, if you see this angle 56 is, if you see this angle QOP is subtended by which arc? This QP arc at the center. And what is the angle subtended by the same arc QP on the remaining part? This 56. So therefore, this angle here that we need to calculate, QOP, must be double of 56. So this angle must be 2 into 56, which is equal to 112 degrees, right? So this was an easy one. So let's write what we have calculated. We have calculated this angle to be 112 degrees. This is 56 degrees. So this is done, QOP. Next, we need to calculate QCP. QCP is which angle? This is QCP that we need to calculate, right? Okay, now the big question is how to calculate. This is an application of angles in alternate segments. Now, if you see, P is a point of contact through which a chord passes, right? So this is angle in one segment, right? So this, if I call this as angle number 1, which one should be angle number 2? What is the angle in the other segment? This one. This is angle number 2. And because we know that angle in an alternate segment must be equal, this must be equal to 56 degree, right? Similarly, through the point of contact Q, there's a chord and there's a chord passing, right? So this must also be an angle. If I call this angle number 3, then 3 and 2 are also angle in alternate segments. So that means this angle must also be 56. And once you know these two angles, you consider triangle PQC or QCP, this triangle here. If you consider, you know the two angles of the triangle, and you can easily calculate the third angle, right? So that is how we do this sum. Any questions on angles in alternate segments? Otherwise, I can proceed to the next concept and the next problem. I'll stop here for today.